Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 13, Spectacle Lens Magnification, Thickness, Slab Off, and Anti-Reflection Coating. These are topics that build upon concepts that you learned about in previous units, and it finishes up what I want to talk about regarding spectacle lenses. So magnification of spectacle lenses involves two components. One is the shape factor, which equals 1 over 1 minus CF1, where F1 is the front surface power, and C equals the thickness of the lens in meters divided by the lens's index of refraction. The other factor is called the power factor, and that equals 1 over 1 minus V F prime V, where V is the vertex distance of the lens. That's the distance from the back of the lens to the front of the eye, the cornea, and it's also measured in meters. And F prime V, as we learned in Unit 12, is the back vertex power. So the magnification of a spectacle lens equals the shape factor times the power factor. Now, you're going to get an answer if it's a convex lens, a plus lens of 1 point something. If it's a minus lens, a concave lens, it'll be 0 point a decimal. So for an example, let's say if you got an answer of 1.234, what that means is the image size is 1.234 times the object size. Another way of thinking about it is the image size is 23.4% larger than the object. If you're very farsighted, you wear high plus convex lenses that make your eyes look bigger. If you're very nearsighted, you wear high minus concave lenses that make your eyes look smaller. Some people require a much stronger prescription for one eye compared to the other, which means that there's a much bigger or much smaller image focused on the retina in one eye compared to the other. And the brain finds it difficult to put these two different sized images together into one fused image. So there are times when we want to influence the magnification of our spectacle lenses. There are three variables that we can change. They are C, F1, and V. If you're very nearsighted, if you work out the math, you'll see that you actually have to increase C or increase F1 in order to decrease the minification, both of which will result in a thicker, heavier lens and an unhappy eyeglass wearer. You can make V smaller by having the person wear an eyeglass frame that sits close to the eyes. Of course, the closest you can get is with a contact lens where V is 0, and that virtually eliminates magnification for both plus and minus lenses. If you're very farsighted and you wear a high plus lens, you can make the lens thinner, you can increase the index of refraction, or you can make the front surface flatter, all of which will decrease the shape factor fraction and decrease the magnification. So to calculate the thickness of a spectacle lens, you need to use the sag, which we learned about in Unit 9. Sag is sagittal depth. And we also learned the exact sag formula in Unit 9. There's also an approximate sag formula, where approximate sag equals h squared over 2r, where h is the semi-diameter of the lens, and r is the radius of curvature of whatever surface we're talking about. And both of those are in millimeters. H is in millimeters and R is in millimeters. So to figure out what the thickness of a lens is, I will give you the formulas, but if you don't want to memorize them, if you draw it out, you can figure out for yourself what they are. So here's an example. we'll draw out the biconvex lens. This is the edge thickness, E. And this is the center thickness, T. And these are our two sags. So the center thickness of a biconvex lens, we'll call them S1 and S2. The center thickness equals S1 plus S2 plus E. And you can see from the diagram how that makes sense. For a plano-convex lens, the center thickness equals S plus E. There's only one curved surface, there's only one sag. For a positive or convex meniscus lens, the center thickness equals S1 minus S2 plus E. For a biconcave lens, the center thickness equals E minus, in parentheses, S1 plus S2. For a plano-concave lens, the center thickness equals E minus S. Again, there's only one curved surface. And for a negative or concave meniscus lens, the center thickness equals E plus S1 minus S2. Remember that all three variables, the sag, the edge thickness, and the center thickness, are always positive numbers. So we all heard about Slab Off in the Karate Kid movie, where Mr. Miyagi tells Danielson, slab on, slab off. Of course, the relationship between self-defense and optics is that you're not supposed to hit anyone who wears glasses. So just wear your glasses and you are safe. So slab off is related to the prismatic effect of lenses, which we learned about in Unit 10. So if you remember, a convex lens can be thought of as two prisms base to base. And as long as you look through the optical center of the lens, as long as the eyeball is right behind the optical center, there's no prismatic effect. As you read and look down through the bottom of the lens, you get a base-up prism effect. And if one lens is much stronger than the other, one eye has to force itself to aim at the same level as the other eye does. And that can create eye strain or headaches or even double vision where you see two rows of print. Similarly, if you have a minus lens, that can be thought of as two prisms apex to apex. And again, as long as you look through the optical centers, there's not a problem. Light does not bend that goes through the optical center. But again, if you read and look through the bottom of the lens, you get a prism effect. And if one lens is much stronger than the other, you get more base down prism in one lens compared to the other. So the optician can actually shave off the stronger base down lens. That's called slab off. And it's done generally for prescriptions where the difference is greater than or equal to 2 diopters in power, lens power. So the procedure is, number one, you calculate the distance power in the 90th meridian for each lens. This is something that we learned in Unit 11. Then you assume that the eye's lines of sight move 1 centimeter below the optical centers, and you use Prentice's rule to calculate the induced prism for each eye. We learned that in Unit 6. And then you subtract those two numbers to find the vertical imbalance, and the slab off is done in the more base down lens. Augustine Fresnel, Fresnel, was a French physicist who lived in the late 1700s and early 1800s. He worked a lot in optics. He invented a new and improved lens for lighthouses that was much brighter than what had been used up until then. Probably saved a lot of lives in avoided shipwrecks. He died at the age of 39, a little older than Mozart, who died at the age of 35. Makes me a little self-conscious about what I've achieved in my life. I guess I can feel a little better knowing that both Fresnel and Mozart never made a YouTube video. So Fresnel came up with several equations regarding reflection of light, and he found that the percent of light reflected off an optical surface as it travels between a medium of index n and air equals 100 times n minus 1 over n plus 1 squared. So if we check out what that means for a glass lens of index 1.5, we find, after plugging in 1.5 for n, that the percent of light reflected is 4%. And that's just off the front surface. The same percent reflection occurs off the back surface of a spectacle lens. So we have a total of 8% of light reflected, and only 92% of the light that hits an eyeglass lens actually is transmitted through it. The general formula for the percent of light reflected off a refractive surface, if you're not dealing with air, is 100 n2 minus n1 over n2 plus n1 squared, where n1 and n2 are the indices of the two substances. So let's draw a glass refracting surface, and we'll draw an incident light wave hitting the surface and reflecting back on itself. Now, to decrease the amount of reflection, we apply an anti-reflection coating to the lens. The coating has a thickness of 1/4 of the wavelength of yellow light. Yellow is just about in the middle of the visible spectrum. And what happens then is the light wave that passes through the anti-reflection coating and then reflects back is 1/2 wavelength out of phase with the light ray that reflects off the anti-reflection coating. And therefore, those two waves cancel each other. And we end up with only about 1% of the light being reflected. Fresnel found that the index of the anti-reflection coating should be the square root of the index of the medium that the coating adheres to. And so scientists tried to find a substance that's as close to that index as possible. And magnesium fluoride with an index of 1.38 is commonly used as an anti-reflection coating.